Hello, everyone. I'd like to share our work, OV3D-CG. It stands for Open Vocabulary 3D Instance Segmentation with Contextual Guidance. In simple words, our research is about helping AI systems see and understand any object in 3D, even if the object was never seen during training. This is very important for fields like robotics, autonomous driving, and augmented reality. Why is this a challenge? Most existing methods can only recognize objects from a fixed set of categories. That works fine for common objects. But in the real world, we encounter countless rare or unusual items. Without context, the AI often makes mistakes. For example, it might look at a computer tower and call it just a box. But if it notices the monitor and keyboard next to it, the AI can reason. This must be a computer tower. That's the key idea behind our work. Context matters. Our framework has two main parts. First, the proposal module. Here we generate 3D instance masks without relying on category labels. We combine a pre-trained 3D segmenter with a SAM-guided segmenter. This gives us reliable object proposals, even for small or rare objects. Second, the semantic reasoning module. For each object, we pick the best viewpoint. Then we create different context-aware representations, such as bounding boxes, landmarks, and SAM masks. These are passed into a multimodal large language model, guided by chain-of-thought prompts. The model then reasons about the object, using both its appearance and the surrounding context to assign the correct label. Now, let's talk about results. On the ScanNet200 dataset, our method achieved 25.4% average precision, beating existing approaches like Open3DS and OpenMask 3D. On the Replica dataset, we also showed strong performance, proving the model can generalize to unseen objects. Numbers tell one side of the story. Let me show you some visual results. In this figure, each colored box or mask highlights an object segmented by our framework. What's important to notice is that OV3D-CG can handle a wide range of object types, even those that are rare or unusual. It can handle simple object names like potted plant or board games. It can also work with attributes, such as yellow chair or purple duvet. It understands specific object types like fireplace or lampshade. And it even manages longer, natural descriptions, for example, a gray fabric chair positioned next to a white desk or a red cylindrical air compressor mounted on a metal rack. All of this shows that our method isn't limited to fixed labels. It can really understand objects the way humans describe them, using both appearance and context. These examples demonstrate that our method is not only accurate in benchmarks, but also produces clear and meaningful segmentation in real 3D scenes. Context-aware reasoning allows the model to correctly recognize and describe each instance, even in cluttered or ambiguous environments. Even more exciting, we tested our system on a real robot platform. The robot could recognize and describe objects beyond predefined categories. It could follow natural instructions like find somewhere to sit or navigate to where the books are. This shows that OV3D-CG is not just a research prototype. It can directly support embodied AI systems in the real world. So what are the main lessons from our work? Number one, context makes a difference. By reasoning about the environment, our system avoids many common errors. Number two, it is flexible and robust. It works well in both benchmark datasets and real-world environments. And number three, it moves us closer to embodied AI, robots that can understand the world in an open-ended way, just like humans do. Thank you for listening. You can find our code and resources by scanning the QR code shown on screen.